morning, my dear friends. Myself Dr. Atul Nagpure, Assistant Professor, and today our topic is Sidgwick electronic theory. This is also called as electronic theory of valency. Now, in the last class, we have discussed that how Werner proposed his theory of coordination, and he tried to explain the nature of bonding and structure in the coordination complexes. And for his work, he has been awarded by Nobel Prize in 1913. This Werner theory was satisfactory for many years, but once the development of electronic theory has emerged in the world, many scientists were trying to interpret the bonding between metal and the ligand in terms of electronic distribution. The first who did this was Lewis. Lewis, what he trying to do? He trying to study the stability of the atom, and he put for his own theory, and he explained that every atom trying to get stable by completing its octet rule. And during that time, in 1927, scientist Sidgwick, he used the octet rule concept of Lewis, and he now tried to explain the structure of the complexes and the metal ligand bonding in the numerous coordination compound. And today that concept, that theory, we are going to discuss. Now, Sidgwick theory says when any metal and ligand react, they are going to form a bonding between metal and ligand species. This metal ion or atom can be considered as Lewis acid, and you know the Lewis acids are electron deficient species. They can accept the electron density, and they can also call as acceptor. However, the ligands molecules are the Lewis bases. They are electron rich in nature, and they can donate electron density, and hence they are called as a donor. If you look at the bond between metal and the ligand, this arrow start at the ligand and end at the metal, and this specific bond is a special case of covalent bond in which only one atom sharing the two electron in order to get the bonding between the two atoms. And this bond can be also called as a coordinate bond, dative bond, or semipolar bond. Now let's discuss. This is, we have octahedral complexes, right? And here I have shown in the pictorial format how the ligand donates electron density to the metal, and this arrow shows electron density has been transferred from ligand center to the metal center, and this is the case of octahedral complexes in which the ligands are arranged in octahedral fashion. Now next, he wanted to understand how the metal gets stable, and he put forward that every metal atom or every metal ion now trying to achieve the noble gas electronic configuration. Now I can say that the driving force why metal is acting with the ligand is that the metal wanted to become a stable, right? And how he can get stable? When he will take electron density, and the moment the molecule or the complex possesses the next noble gas electronic configuration, in that case this will be a stable. By using the same logic, by using the same theory, now he gave the effective atomic number rule. This effective atomic number rule is nothing but a total electron at the metallic center, and total electron includes the electrons of the metal atom or metal atom plus total electron gain from the ligand. So this expression becomes effective atomic number is equal to Z minus N, where Z is atomic number of the metal and N is oxidation state of the metal, and the two, as you know that if I represent this bond means two electrons. So if I take more than 8 ligand, every ligand will donate the 2 electron. That's why 2 into Cn means coordination number. The same logic he applied, and he suggested that if AN is equal to inert gas configuration or noble gas configuration, that resulting compound or the resulting complex will be the stable one. Now based upon that, now we'll discuss how metal ion form the complexes and what is the EAN for them. I'm going to make a special lecture on the EAN, but in this lecture we'll just discuss the basic logic behind this EAN concept. So now let's move towards further, and we're going to form many complexes, and we'll try to calculate the effective atomic number, and let's discuss that what are the driving force behind the reaction between metal and the ligand. So let us take that we have hydrogen here, and we have lithium, and we have sodium, and we have potassium, right? You know, here potassium, then we have calcium, here we have magnesium, and we have beryllium. Okay, so after calcium, 3D series will go to start, and let's start with the scandium, right? Scandium, titanium, and let's say we have manganese here, right? Manganese, and we have zinc. And after zinc, what come? After zinc, we will get a krypton, right? Which is the noble gas. Now after that, a scandium, this is 3D series. Now here yttrium, 4D series. Now a lanthanum, 5D series, right? So below manganese will be having technetium, and below technetium will be having rhenium in a 5D series. And here we have cadmium below zinc, and here we have mercury. See, this will end at xenon and end at the radon, right? So if you look at very carefully this 3D series, so I can say this is actually a 3D series. This is a 5D series. This is actually a 4D series, and this is a 5D series, right? And 3D series start with atomic number 21, right? And this is 22, and manganese will have 25, and this is the 30. Am I right? And krypton will be having a 36. Xenon, this is 54, and radon is 86. Now let's discuss that why complex form. Okay. Now again I will mention here manganese we have, then we have ferrous, then we have cobalt, then we have nickel, and then we have copper. So I will respect to atomic number and mentioning here 26, 27, and 28, 29 is copper. Now what Sidgwick suggests, why metal reacted? Because they wanted to become stable. Now let's say we have now iron. Okay, now we have iron. If I take iron here, and in order to achieve the krypton electronic configuration, let's say that iron wanted to become krypton, right? So for that I am discussing one complex FeCO5. This is pentacarbonyl iron complex, in which iron now has a zero oxidation state. Now apply EAN. So if I apply EAN, what will be having? Electron at the metallic center. So iron 26. So you can write down here. We have iron. We have 26, and carbonyl is a more ended ligand. So one ligand will give 2 electron. So 5 into 2 means we have 10 electron. Okay, and therefore we have 36. 36 means nothing but a krypton electronic configuration. That means I can say now that since this complex possesses total electron at metallic center, which is equal to 36, nothing but krypton electron configuration, and that's why it's a stable. Okay? Now let's move further. If I take nickel here, imagine if I want to get nickel to achieve the krypton, right? Now let's discuss for nickel we have nickel CO by 4, right? Nickel CO by 4. Now nickel CO by 4, if you calculate the total electron density, what we have in this complex nickel is actually a zero oxidation state. Am I right? Okay. Now if you find out that nickel electron is 28, we have 4 modern-date ligand, so 4 into 2, it becomes 8. Now again we have a 36. Please look at very carefully. And again nickel carbon is a stable complexes. This is the case for the sum. Now I am just giving one example. Let's say we have now iron complexes. We have K3 FeCN by 6. FeCN by 6, and a cyanide is anionic ligand carrying minus charge, 1 minus charge. Now if you calculate the oxidation state, you can realize that this complex has oxidation state plus, means iron is in +3 state. Okay. Now if I calculate now En of this complex, so electron at the metallic center, iron is 26, you can see here 26 iron. Now 26 minus 3 will get a 23. Z minus N, remember Z is 26 and N is 3, so we have a 23. Alright. Now cyanide as I told, modern-date ligand, cyanide ligand will give the 2 electron, and therefore will be having here 6 into 2, that is mean 12, and this is become 55 electron total. But my friends, so far we have seen the complexes in which we are getting a krypton electronic configuration. That means this 3D series element, what will do? The 3D series element will try to achieve the electronic configuration of chromium, and that's why that also driven the coordination number. So what it suggests? It suggests that whenever iron is in 0 state, it will go to form a complex with 5 coordination number, whereas nickel in a 0 state will form the complexes with coordination number 4. Now since getting a krypton electronic configuration, but once we move towards this complex, you will realize that total electronic configuration or total electron density at the metallic center is equal to 35. Clear this point? Now let's discuss our next example, and now we'll try to explain iron complex here. Stability of the iron complex. Now taking a same parallel example, but now I am going to change the oxidation state. Let's say we have FeCN by 6, right? And here you can realize that oxidation state of iron is +2. Now let's again do it, the same thing. Iron, how many we have? We have 26. So Z26 minus 2. It will give a 24 electron. Cyanide again anionic ligand will give a 2 electron. Therefore 6 into 2 we have 12, and therefore it's become a 36 is nothing but a krypton electronic configuration. Now the questions come. If I discuss the stability of this complex and this complex, by Sidgwick theory, you will say, sir, this complex is more stable since this complex has 36 electronic configuration which is resemble to the krypton. This complex you will say stable than this. The story is different. Because in the real case, stability of this complex is slightly higher than this, since the iron is in +3 state, here iron is in +2 state, and that concept, that behavior cannot be explained by Sidgwick theory, and that is the limitation. In order to explain the stability of the complexes, we have to move towards valence bond theory, crystal field theory, or ligand field theory. This is what the suggestion. So if I discuss now 3D series, now let's move towards 4D series. Okay, I'm just giving one example of the iron copper complex here. Say we have copper complex, we have tetraamine copper +2 complex, and copper belongs to 3D series. Copper +2, right? So Z, what is Z value? We have 29. 29 minus 2. So 29 minus 2, 27. Electron at the copper +2 ion. Amine is a neutral ligand. Again, donate the 2 electron. Therefore, this is, I can write 4 into 2, become 8 electron. Now again find out. What is the value of this? 27 into 8. So we'll be having now a 35. Am I right? 35. Again you will confirm that this may not be the stable complexes. So if I put in the overall discussion, I can say that 3D series element will try to achieve the electronic configuration which is equivalent to the chromium 36. Right? This discussion was related to the now 3D series. Now if I move towards 4D series, so 4D series start with the yttrium, and then we have technetium, and then at the end at the cadmium. So if I take any metal from this 4D series, the conclusion will be based upon this theory that this metal ion, metal atom will try to form a complex, and this complex should have the xenon electronic configuration in order to get the stability. Similarly, I can say from 5D series, the 5D series metal will try to get the stability in order to get the Rn electronic configuration. So I can say simply here, the 4D series element will try to achieve the electronic configuration of the xenon with 54 electronic configuration, right? And the 5D will try to achieve Rn with 86 atomic number. But now so far we have seen that this stability, but problem comes here. We cannot discuss the stability of any complexes only based upon the effective atomic number, and this is the serious drawbacks of the Sidgwick electronic theory, because in those days we did not form, or scientists did not form many complexes, and this theory was limited to only few complexes. The effective atomic number rule generally followed for metal carbonyl complexes, but it is not the case. It should be followed by all the complexes. This is not the case, and hence this is the serious drawbacks. Now what he did, the Sidgwick was not able to also explain the directional nature in the metal ligand bonding. He does not throw any lights toward the geometry of the complexes. Moreover, he does not explain that which metal orbital is involved in the bonding. We have P or D or F, and does not explain also the role of the ligand in the complexes. Furthermore, the magnetic nature, the color property was not discussed at all. But generally, once we use this theory, we generally say that this Sidgwick, he was trying to explain the nature of the bonding and structure of the compound based upon the electronic theory. Even though I have discussed there was many drawbacks in this theory, but the contribution of the Sidgwick cannot be ignored at all, because we are discussing the theory at the earlier age when the coordination chemistry, when coordination compound just emerged, right? And we need to explain, we require some theory, we require some possibility to explain the bonding in the complexes. So this is what all about the Sidgwick electronic theory. In the next lecture, I'll again explain the effective atomic number by taking a various example, and in that I will specially discuss some ligands which are not common, some complexes where are rare in nature. So I hope that you love this Sidgwick electronic theory. We have to give credit to the scientists Sidgwick, like Lewis and the Werner. I hope that you like this lecture. If you have any question, give me reply. Good luck. Thank you for watching. Please subscribe my channel so you can get a more updated video. Thank you for watching.